We assume we've got a rectangular region of the xy plane, and we're trying to just depict a general function of two variables. So you're going to have a z coordinate. For each point, you evaluate the function, you get the z value, and that's going to give you the length of this segment here. So here, 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 and here, we have z values. Then I just draw kind of an arbitrary curve between above each edge of this rectangle, okay? So now what I have, for example, here, if this is the y direction, then I have a plane parallel to the yz plane, and we see the curve we get when we cut the graph of this function with that plane. And, a plane parallel to the yz plane through this point, or this point, or this point, or this point, okay? And then we do the same thing back here, and now we see the curve that we get when we cut the function there, okay? And similarly here and here. Then we just kind of morph this curve toward this curve. So I'm just going to say, okay, this goes from here, and maybe this looks like this. And then we morph this curve into this curve, looking something like this, and maybe like this. And now we have kind of a wavy surface that could indicate any plane, or any function, okay? We might have a function that looks like this, okay? Now let's say that we just now take a point here, somewhere within this rectangle down here in the xy plane. Okay? And then we project this point up to the surface. Okay, we get a point on the surface. And now what are our curves going to look like in this direction and in this direction? Using a different color, we see that the curve above this line here, the xz plane above this line that goes in the y direction through this point, would start up here, and it would go to here, and it would probably look much like this one. Matter of fact, it might even be this one, which means when I projected this point to here, I screwed up. Okay, so let's go ahead and project the point up to here. It just turns out that this appears to match up with this contour line, or that's not a contour line, but this curve on the surface. It corresponds to an xz plane through this point, a yz plane, okay, for a given value of x, okay? Well, in that case, the point on the curve that corresponds to this point well, the slope of the curve at this point would be the partial derivative with respect to y. Okay? So, if we do a tangent line here, which is a little tough the way the curve is oriented, I could have made a better choice, but, okay? It's a partial of f with respect to y at this point. So this point, I'm going to call that my point xy. So the slope of this line segment here is the partial f with respect to y at point xy, the point I've chosen to call xy. Now I could have called that x naught, y naught, but it's a general point, so I'm just going to call it xy. Okay? Then I can do the same thing with the plane directly above this line, on which y is constant, right? X is constant in this line, y is constant on this line. So I project this point up to the curve, and project this point up to the curve, and then I sketch what I think the curve might look like here. And I project this point that way. Actually, the curve has to go through this point. I missed it. Okay? So I kind of screwed up the picture. Let's see if I can quickly repair that without smudging up the whole thing so that nothing is recognizable. I probably got too much of this stuff on now. Let's just get rid of it. Okay, let me just kind of see if I can get rid of that purple. That works pretty well. That can be beautiful, but anyways, in the first place. So, again, this line goes through this point, so if I project this point up to the corresponding curve in this plane, it has to go through the point, and I should have paid attention and made it do that. So, looks something like this. That make sense? So based on the way this is shaped, what's your slope there, positive or negative on this curve? Yeah. It looks like it's going up there, right? If you were walking this curve, you might go down just a little bit here, but for the most part you'll be going up until you get maybe up to the very edge, and then maybe you're going down a little bit. Okay? So we have make it a little longer. Is the partial with respect to x evaluated at xy. Okay? So there we have a picture. Now we could even expand that picture a little bit. So now let's say that here's our point, okay? And here's our y direction of the point down in the plane. This is the point on the curve, okay? So we can say that, okay, well, let's say our slope here is kind of like this, right? And that's above this line. So that little segment there corresponds to this interval of the line, okay? And the slope, well, I just take a segment parallel to this one. And now we have a triangle whose slope is the slope of the tangent line, right? Because this is a tangent line, okay? And then, just to smudge the picture up completely, we have this tangent line, right? And this tangent line goes through this point. It lies above an interval down here. And if I want the slope, well, then I have to take a segment parallel to this one. And there is the triangle that gives me the slope in the x direction. Okay? The partial derivative with respect to x. Now you're going up in this direction. Traditionally the x direction will be out this way. So really your slope is negative, but you know, in the direction that we're looking, we're going up, right? So that'd actually be a negative slope, just because you're talking about this direction. Still, you've got the two triangles that give us the slope, and they intersect at the point where these two sloping segments intersect, and I kind of got that right. Okay? So now we can see the partial derivative the slopes of triangles. And that's kind of an important picture if you understand what you're seeing and if you can sketch it, okay? Now, you can just look at it here, though. You think, okay, that's a negative slope. If x is in this direction, then that's a negative slope. Okay? Make sense?